In the distance, a whisper is heard. Silicon Carbide. Yep, just the mention of the legendary name sends shivers up the spine of any self-respecting MOSFET connoisseur. The mystery of silicon carbide has spread through these hills for decades. A dark-clothed figure who would suddenly emerge from the night with a shout of carborundum, raising switching frequencies, increasing power density, and turning ordinary MOSFETs into veritable superheroes. Hi. I'm Amelia Dalton, host of Chalk Talk. Okay, maybe silicon carbide isn't exactly the stuff that legendary engineering superheroes are made from, but it turns out that it's a pretty fantastic material for certain types of transistors. And if you learn how to use the properties of silicon carbide to your advantage, well, you just might come off as a hero yourself. Today, I'm talking with Xuning, Zhang, and Sujit Bangeree of Monolith Semiconductor, a Littelfuse technology partner, about how to design silicon carbide MOSFETs into your next project. Listen up, you'll be glad you did. And before we get started, don't forget to click that link. There you can find out even more information about silicon carbide MOSFETs. Welcome, Sujit and Xuning. Thank you so much for joining me today.
It's a great pleasure to join you.
Nice to meet you, Amelia.
Okay, Xuning, I'm designing power systems, and I've been hearing about silicon carbide for a long time. But for people in the audience who don't know, what's the deal here? What's all the excitement about? Why would I want a silicon carbide device, say, in my inverter or converter or motor control design?
Okay, the material silicon carbide shows superior performance over silicon devices in terms of high voltage blocking capability, lower conduction loss, lower switching loss, and also the capability of working at a higher temperature, which all help us to reduce the size, the cost of the converter. By having lower conduction loss and switching loss, we can reduce the size of the heatsink. And also with the lower switching loss, it also helps us to be able to increase our switching frequency, which can dramatically reduce the size of all the inductors, capacitors. The high temperature operation capability also allows us to have a higher margin for the whole thermal system design. It helps us to reduce the size of everything in the converter. It also increases the efficiency of the converter, make the whole performance of the power converter be much better.
Okay, great. Those sound like things I would want to do in my power system. And when we're talking about silicon carbide devices, we're really talking about things like transistors and diodes, right?
Correct. For silicon carbide devices, we are mainly offering the unipolar devices, which is for switches, is MOSFET, and then for diodes, we're offering the Schottky diode. So the superior performance of silicon carbide MOSFET is mainly the lower switching loss and lower conduction loss, which allow us to reduce the switching loss almost 90% over silicon IGBT. And also for silicon carbide diode, the main benefit we can offer is almost no reverse recovery loss. That whole thing is a real headache when you design a converter. When you use a silicon carbide diode, you don't need to worry about that. There's no reverse recovery loss in a silicon carbide diode.
Okay, now, Sujit, that seems like a clear win to me compared with that other silicon we've all been used to using. So why isn't everyone using silicon carbide already? There's got to be a catch in here somewhere.
Actually, Amelia, silicon carbide has always been recognized as the semiconductor that can revolutionize power electronics. But unfortunately, it has always been a niche due to limited availability and high cost. So Monolith was founded in 2012 with the aim of bringing silicon carbide high voltage switches from the niche markets to mainstream and to apply them to industrial and automotive application and drive widespread adoption. The goal was to bring the best practices and learning from rich history of silicon power semiconductors to the world of silicon carbide. The key to great success of silicon power semiconductor is being able to manufacture at very high volumes, billions of units per year at high yield and reliability, extremely low single-digit ppm level of failure, and this is what takes to penetrate high volume mainstream applications. It's not just the device with the best performance. We are already armed with excellent material properties of silicon carbide that Xuning talked about earlier. What we need to focus on is how we design and a manufacturable process with which we can make these devices with high yield and reliability. In order to do that, you need to use existing silicon fabs which are already manufacturing silicon at high volume for automotive. And that's what we have done. So we are using an existing 150mm silicon CMOS fab to manufacture our devices. And we have been reusing established CMOS process and minimize the need of special tools, which allows us to ramp up volume very quickly when needed and use minimum amount of capital, which minimizes the depreciation and cost of manufacturing these devices. And that's how we can provide silicon carbide devices at very high volume with low cost and extremely high reliability that is well known in automotive applications.
Now, Sujit, I understand you guys are partnering with Littelfuse, so explain to me a little bit about what this partnership is all about.
Right. As I talked about earlier, these go into industrial and automotive applications which have very long design cycles, and customers really expect to see a company in business for a very, very long time, and they expect a lot of very strong support and having deep expertise in managing whole manufacturing process. Now, that's difficult for a small startup to do that way. So we knew from the very beginning that what we wanted to do is bring deep power semiconductor and application expertise. That's what we bring to the table. But we wanted to partner with an existing well-known business in the field that already has experience in supporting both industrial and the automotive customers. And that's what Littelfuse brings to the table. So Littelfuse is a well-known name that brings industry-leading customer support. They are very used to manage a global manufacturing and supply chain. And they do have a diverse technology portfolio from fuses to semiconductors, both power semiconductors and also protection semiconductors. And now they have decided to get more into this power semiconductor space, partnering with Monolith. Monolith brings the technology and the application expertise. We bring both the high performance silicon carbide MOSFETs and diode and our manufacturing expertise that I talked about in the 150mm fab. And Littelfuse enables us to take this technology and spread it globally. So we sort of like to put it in a way, the overarching thing for this whole Monolith Littelfuse partnership is we want to put customer first. So what we like to say is defined by customer, developed by Monolith, delivered by Littelfuse.
So explain to me in detail what exactly that means.
So essentially, if you look at it, Monolith brings to table primarily started with our expertise was with the semiconductor technology. So Monolith has very deep expertise in both development of silicon carbide technology and how to deploy it in the fabless model in 150mm CMOS fab. The other value we bring to the table is a very strong application support. Now, in order to be successful in getting a new power semiconductor into the market, just having the semiconductor technology and the technical expertise is not sufficient. As I said, Littelfuse brings a global expertise, but also what it brings us is that it also gives us the expertise in packaging technology we need. Littelfuse already have developed power modules and different kind of packages. Littelfuse brings that into table from the packaging technology. Design support is absolutely critical. As we'll see in the next part of the presentation, the silicon carbide devices, if you put it into your system, you need to design your system differently. You need to have some extra effort to design the silicon carbide into your silicon-based system. Design support is absolutely critical. While Monolith does have the technical expertise to do that, in order to deploy it globally to all the customers, we need Littelfuse. So we will bring the design support together with Monolith and Littelfuse. Finally, availability, the supply and the infrastructure of all the other components that go around the power semiconductor, including protection elements, gate drivers, analog components. Together, Monolith and Littelfuse will strive to bring the whole infrastructure up so that you not only get the silicon carbide MOSFET and diode from us, you also get the application support and you also get the supply and infrastructure. So we are going to walk you through the entire journey, not only from when you start designing silicon carbide into your system all the way to the point where you're manufacturing it at high volume and you are delivering them to your customer. That is our commitment to you.
Okay, so circling back to you, Xuning, sounds like I don't just take my existing design and swap out the silicon MOSFET for silicon carbide then, right? I'm gonna need some help re-engineering my system to take advantage of this.
Exactly. Previously talk about the benefit of silicon carbide devices. Super fast, it really helps you to improve the efficiency of your system and also to reduce the size, which increase your power density. However, the super fast switching speed also creates a lot of problem in the system. A lot of detail need to be considered in the system design. So that's where, for example, it needs you to minimize the parasitic inductance in your whole power circuit, and also needs you to minimize any noise coupling, and it also needs some precise measurement of all your voltage, current things to make sure that you can get the correct information for your control. Also, when you increase the switching frequency, you need to redesign your system not only just for the power part, you also need to redesign all the passive components, your inductors, capacitors, and also your heat sinks, everything matching with the high switching frequency design when you're using carbide devices. For example, we're talking about the switching behavior of silicon carbide devices. Here is an example of a typical switching voltage and current waveform of using silicon carbide devices. And here we're talking about around 80 volts per nanosecond dVdt and 5 amps per nanosecond dIdt during the switching, which is around at least 5 times higher than the typical IGBT switching speed. All these high switching speeds help us to make the performance of our converter superior compared with silicon IGBT based solutions. However, it also creates a lot of problem. For example, this high dIdt will generate a high voltage overshoot, which actually limits the voltage you allow to use for a certain voltage rated devices. And for example, for 1200 volt devices, probably you can only use 800 volts, but you're losing a lot in that voltage rating. More than that, all these high switching voltage and high dVdt and all this ringing generates conductive common mode noise that propagates error in your system that messed up with your control or messed up normal operation of your system. Also, this high dIdt and dVdt make it very hard for the measurement or for your control circuit measurements, the sensing. It makes it very difficult to get the correct information to be used in your control system. Also, this high dIdt will have some radiated noise generated surrounding the power circuit that actually coupled with everything surrounding your power converter. It may make your cell phone lose, for example, or some other system messed up in the normal operation. And such things make it very hard to design a power converter using the silicon carbide devices.
Okay, so it seems like these are all theoretical problems. How do they really show up in my real world design? And how is that different with silicon carbide from what I've seen with silicon?
That's a very good question. Actually, the answer is there's no significant difference. For example, you make a wafer for all of your devices, you package it in your whatever packaging you use, and then you put it in your circuit. This packaging and power stage design layout all add parasitic inductance and capacitance to your circuit. These are all the same for silicon and silicon carbide devices. These parasitic inductance and capacitance added to the circuit may be the same value. However, we are talking about more than 3 times higher switching speeds on silicon carbide devices. Then these voltage overshoot, common noise issues, or radiated noise issues will be 3 times more severe for silicon carbide devices than silicon devices. That's why we're saying that these application design are limiting the performance of silicon carbide devices. They may not be an issue for silicon devices, but they become a big limitation for silicon carbide devices.
Can we dive into some more detail about that? How does this look in my circuit?
Yeah, for the parasitic threats, we have identified 3 main threats that limits the performance of silicon carbide devices. One is the common source inductance, which is the coupled inductance between the gate and power circuit. It will limit the device switching speed and increase the switching loss. The second threat is the power loop inductance, which is the parasitic inductance of the circuit flowing through the power devices and the load. It will induce a high voltage spike during the turn-off transient of the switching. And the third threat is mainly the Miller cap, which is the capacitance introduced by the package and layout between the gate and the drain of the device. It can lead to an inadvertent turn on or shoot through during the switching and then bring a catastrophic failure to the whole system.
So Sujit was talking about support for my design process. Let's talk about some specifics about that. How does your team help me re-engineer my design? And do I just show up on your doorstep with my scope and board in hand?
That is the way we want to serve all the customers. We can help you to solve the problems you have. To do that, we actually have fourfold application support. We define 4 different categories for our application support. We start from the characterization of the devices. We'll help our customer to understand the switching behavior of silicon carbide devices. We provide the dynamic characterization platform. With that platform, the customer can understand how silicon carbide devices switches. We can capture the very detailed switching waveform of our devices under different conditions. On top of that, we also provide different driving solutions for different purposes. For example, we'll try different versions of gate drivers for different customers with different requirements to help them to drive our device easily and safely, and also to get the max benefit off of our devices. The third category of our support, the reference power stage. In here, we will provide some plug-in and play phase lag with full design of driving and thermal. So the customer can do a very quick design in using our device. So they don't need to worry about the power stage design anymore. So they can directly use this reference power stage to build his own system to see what is the main impact of using our device on their system level design. And the fourth category is the demo converter. So we will also release different reference converter design for different targeted applications to show our customer the benefit. If you use silicon carbide devices, what is the revolutionary change for different applications?
All right, I'm a dev kit kind of girl. Have you got any kind of development board or kit that can help me get going or get started?
Here's one dev kit for you. We call it the Dynamic Characterization Platform. This platform is developed for all customers to understand the device switching behavior. Some key features of this platform is this have a high voltage, high current pulse load capability that allows the user to characterize the device switching behavior under different load conditions. It has its dedicated design for different device packages. For through-hole, for SMD package, we will have different versions of this similar design for customer to characterize devices with different packages. This dev kit is designed for pulse testing. There's no need for thermal solutions considered for this dev kit. And it has its own optimized layout design for both gate and power loops that ensure it to give the customer an accurate and consistent measurement of the switching behavior of our devices. And it's very easy to use. We call it dumb operation, so it's very easy to operate this to get the accurate measurement of our devices. This dev kit is a good option to characterize the switching behavior of silicon carbide devices, and also it's very good to use it to verify the datasheet information we provide you. And this dev kit can also perform as a platform to understand device performance. But the main reason why we release this is to accelerate your converter design using silicon carbide devices.
Okay, that's cool. Have you got a schematic for this thing?
Yeah, this is the one. For this dev kit, we actually have a half-bridge configuration for the power stage where the user can characterize either diode or MOSFET or both for either high side or low side. And also we give a 2 separate gate driver for the high side and low side switches, which allow the user to switch devices at different positions. And also we use a very simplified gate drive structure to allow customer to understand the switching function of the devices in a straightforward way. It also have a high frequency isolation. Both digital isolator and high isolation power supplies allows us to control the conductive EMI noise propagation to avoid any coupling between the power stage and the control stage. It also have a optimized board layout to prevent any near-field coupling between the power stage and the control stage.
All right, so when I want to kick the training wheels off and design my own board, what do I really need to think about?
Okay, several details about this board present. One is about the layout design, because this one may not be a very important feature for silicon IGBT design, but it is very important for silicon carbide MOSFET design. In this design, some design guidelines we have here, we want to keep the gate loop as small as possible. Meanwhile, we will suggest our customer to lay out the devices to make sure the commutation loop is also as small as possible. Meanwhile, we also prefer to have a decoupled power loop and gate loop so that there will be a minimum coupling between these two loops, so that during the switching there will be minimum noise coupled from power loop to gate loop. These design guidelines is required for very reliable and accurate dynamic calibration. That's why we implement all these design details in the dynamic calibration platform that allows our customer to have a very accurate measurement of the switching behavior. Meanwhile, these design guidelines is suggested for our user for a converter power stage implementation. So another feature we added to this platform is the EMI Propagation Control. Everybody is worrying about the EMI issue brought by the high switching speed of silicon carbide devices. We identified this as the common noise propagates through the gate driver circuit from power stage to the control stage. And we see this problem as a common noise. We model the common noise source as a current source, and the conductive common noise induce digital control circuit function. So in order to protect the digital control circuit, our approach is trying to differentiate the propagation path impedance for common noise through the gate driver power supply path and the gate signal path. We intentionally maintain a higher impedance for gate signal path to block common noise propagates through this path, and we also intentionally lower the impedance of the gate driver power supply path to bypass the common noise so that we can minimize the common noise current propagates through the driver circuit to the digital control circuit. Using this way to protect our digital control circuit from the noise generated by the switching of the power devices.
Okay, so what about this driving circuit thing? It seems like that's going to be way more complicated for silicon carbide. Is there anything that helps that part of my design be easier?
Yes, to make our user to have a easy gate driver circuit design, we will provide different gate driving solutions for different purposes. Currently, we will provide two versions of gate driver circuits. One we call the economic version, which actually have only the basic driving function with no protection. This one has the optimized layout design and a verified EMI performance. The main purpose of releasing this version of the gate driver is to help our customer to understand the driving design details for silicon carbide devices, and since this one does not have any protection features, the users still need to design their own protection features surrounding this basic driving circuit. And we also provide the standard version gate driver, which actually we predefined all the protection features, including the DCP protection, under voltage lockout protection, active Miller clamping protection, and also the stop turn off during the protection action. And for this gate driver board, we will have a predefined signal interface, and also on our website, you will find all the detailed schematic and the layout design as a reference to our customer.
Okay, so can you give me a few more details?
Yes, for example, for the economic version gate driver, we use a digital isolator plus current booster solution just for the basic driving functions. This gate driver can work up to 200 kHz switching frequency to drive our devices. There's no protection, so the user has to implement their own protection. The design has been verified internally in our lab in the converter design platform for many hours of continuous operation. It has the same interface with our standard gate driver. For the standard version gate driver, we have actually two different sub-versions of this gate driver. We have a optical coupler solution and also a digital isolator solution for different preference. This gate driver can switch up to 200 kHz switching frequency to drive our devices. We pre-implemented different switching protection features, including the DCP protection, the under voltage lockout protection, active Miller clamping protection, and also the soft turn off feature during the protection actions.
All right, those look pretty well defined. How do I get started using those?
So to help our customers to evaluate our gate driver easily, we also have designed this gate driver evaluation platform. So for this platform, it's actually a half-bridge configuration with easy swapping connectors to connect the different gate driver solutions. And we provide also different measurement points for driver performance, for example, at the VGS signal and the VDS signal of the devices. And it also have the optimal power loop design, so the user do not need to worry about the limitation of the device performance due to the power loop design. It also has the capability of continuous switching operation, so the user can evaluate the continuous switching performance of the gate driver. For example, the EMI performance or noise blocking performance of the gate driver circuits.
All right. I am a Silicon Carbide fan. Let's wrap this thing up. Can you give me a quick overview of what we've discussed?
With the partnership between Littelfuse and Monolith, we're here to provide you the Silicon Carbide MOSFET and diodes with leading performance. Meanwhile, we are also providing you the dedicated application support to use our device easily and also to help you to extract the maximum benefit out of using Silicon Carbide devices.
All right, I'm ready to get started designing. Where should I go for more information?
So for samples and more information, you can go to mouser.com.
Great, I think that's all I have time for today. Thank you so much, Sujit and Xuning, for joining me today.
Me too. It's a great pleasure to talk with you.
And before we go, you didn't forget to click that link, did you? There you can find out even more information about Silicon Carbide MOSFETs. For Chalk Talk, I'm Amelia Dalton from eejournal.com. For more Chalk Talk, head on over to the Chalk Talk section of EE Journal or check out YouTube, keyword EE Journal.